before. Take a little bit of a breather here. Okay, and again, anytime I use the textbook, I will put it underneath this camera so that everybody can see it. I'll reference page numbers for you. So if you want to look at it through the electronic version in my math lab, you certainly can. You can find that page. Okay, section 2.5, continuity. Continuity. Lots of I's in this word. Continuity. Continuity. Pretty neat word. So really what that means is trying to determine if a function is what we consider continuous or not. So we're looking for continuous functions, and so to put it in one word, we call it continuity. Okay, so just a little informal beginning on this when we talked about something being continuous is I'm going to actually go straight to the textbook and read what they have written, because they do a good job on page 73 in the textbook of kind of prepping you for this section. Okay, page 73, an informal beginning. And at the bottom of this section, it's a lower part of this page, it says, okay, we plot functions in laboratories and data collected from fields, and we plot these points, and then we draw a line through them, making an unbroken curve to show that the function's values, what they have been at times and what they'll be in the future. So, you know, scientists will go out there and collect data, and they'll plot points on a piece of graph paper, and then they'll strike a line between them. So then they can make projections between the points according to the data they've collected. So we run lines through everything like that, through data. So when we run that line, we are assuming that we are working with a continuous function. So this is the new thing, continuous functions. So that its outputs vary continuously with the inputs, and we do not jump from one value to another without taking on the values in between. So there's no dramatic changes. It's going to be a nice, smooth, continuous kind of system. And then down here it says, intuitively, any function whose graph can be sketched over its domain in one continuous motion, meaning if we can sketch the graph without lifting our pencil off of the piece of paper, then this is an example of a continuous function. So this is a really nice way of defining a continuous function. If I can put my pencil in that piece of graph paper and run that line without ever picking up the pencil, then it's going to be a continuous function. So, of course, what are our problems going to be? Let's think about this. For the function to be continuous, I do not pick up my pencil. Okay, so continuous, informally, a continuous function can be sketched or graphed or drawn without picking up my pencil, without lifting the pencil from the paper. Very informal, but an excellent, quick and easy, very straightforward way of understanding what it means to have a function that is continuous. So this is really simple. You come in here, here's an XY axis. If I can draw a graph without picking up my pencil, that graph is a continuous graph. Okay, that's continuous. So thinking very simply about drawing the sketch of a graph, can you think, if you were working with a pencil and a piece of paper, when would it not be continuous? When would you have to lift your pencil? That's right. The minute you have a hole, the minute you have an asymptote, anytime you have a jump. That's like a jump. That's still another jumper. A jumper, I call it a break, either way. These are the big guys. And like these are the ones we've been focusing on really in depth about talking about limits. Okay, this is where we go. These are the big important parts where there's always an issue to be discussed. So it's not continuous. This is where you have to pick up the pencil when you're sketching a graph. So you can see where this is leading already. So asymptotes, and really this would have to be a vertical asymptote. If it was a horizontal asymptote, you would just hug it and keep going. So really a vertical asymptote. So you're right. These are the things that cause us issues. So now let's go back down here and let's kind of look at some examples, what we're going to run into in this section of this textbook. Okay? And a more formal definition. see if we can read the definition. Okay, I'm going to pull the example one from the textbook on page 74 and take a look at this. And I have written all over the book. It's probably do not write in your books because you will never be able to sell them back, okay? But you can see I've scribbled all over this book. Find the points at which the function f in figure 2.35, over here where I've scribbled all over it, is continuous, and the points of which it is not continuous. And they do a really good job of kind of organizing this by where it is continuous and where it is not continuous. So it is continuous at x equaling 0. So right here, it is continuous. It's like the left endpoint of the graph. So it's considered continuous at a filled circle at the endpoint of the graph. It is continuous at x equaling 3. So here we have, kind of a point in the graph or a corner kind of in the graph, but the circle is filled in, so we're still happy. It's still continuous. I could do this without picking up my pencil. And then it says where c falls between 0 and 4, okay, where c falls, or your x value falls between 0 and 4, but not at 1 and not at 2. So we're continuous. We're moving along, and oh dear, I have to pick up my pencil at 1. So at 1, I lose continuity. Moving along, oh dear, here at 2, I have to pick up my pencil to fill in that one up there. Okay, so I lost continuity at 2. Moved up to 3 with no problem, and down to 4 with no problem. But right here at the open hole, the open circle, I have to pick up the pencil to fill it in at a hole down here. So at this point, at 4, it is not continuous. Okay, to draw the little open circle, it's not continuous. So it says less than 4, not less than or equal to it. Okay, another interesting thing they kind of go over here is it's continuous at 0, and if it's continuous at 0, then the limit of the function is equal to the value of the function at that point. So over here, the limit coming in from the right-hand side is 1, and the function value, the filled-in circle, is also at 1. At 3, the limit of the function, as I move to 3 from the left and the right, the limit of the function is a height of 2, which is the filled-in circle, which is also the function value f of 3. So they're showing you that when the limit and the function value are the same, you have continuity. Where is it not continuous? Well, it's not continuous at 1. Well, duh, of course, we already said that, okay? When you come into 1, the limit, if you're coming in from the left and you're coming in from the right, the limit from the left is 0 and the limit from the right is 1. So the limit in general at x equals 1 does not exist. It's a break in the graph. It's not continuous. At x equaling 4, it is not continuous. There is a break in the graph. The limit of the function at 4 is a height of 1, but the function value where it's filled in is probably a half. So the value of the limit and the true value of the function are not the same when the x value is 4. So then it comes down here and it says something important that I highlighted. It says to define continuity at a point in the function's domain, we need to define continuity at an interior point and continuity at an endpoint. Well, the interior points, are in the middle. The endpoints are occurring here and here. Okay? And so what does it say about that? Well, it really doesn't talk about it until you get down here underneath the definition. And it says if a function is not continuous at a point, we can consider it discontinuous at the point. If a function is right continuous at a point in its domain, If a function is right continuous, meaning it's continuous from the right at a point in its domain, if the limit equals the function value. Okay, see if I can put this in. In other words, your endpoint is going to represent continuity if your circle is filled in, meaning it is equal to the function value. If your endpoint is an open circle and your function value is elsewhere, then it is not continuous at the endpoint. Okay? So your endpoints only give you continuity if you have a filled circle or a function value equal to the limit at the endpoint. And they do a good job when you read through it slowly and you think about it. It does make sense. So here's the lovely definition. An inside or an interior point. A function, f of x, is continuous at an interior point c, some x value equal to c, of its domain if the limit at the x value of c of the function is equal to the function value there. Okay? So in other words, if the x value is 3, up here, then the limit as the function is approaching 3 is this filled circle 2. And the function value is also 2. So it is continuous here. But if you take the x value of 2, the limit of the function at 2 is a height of 1 where the hole is. But the function value at 2 is 2. So it's not continuous at this point because the limit and the function value do not agree. And then we go into the left and right endpoints, again stating that if it's a filled circle, it's going to be continuous, and if it's not a filled circle, it'll be discontinuous. So you might have to study that page a minute to try to really get a full comprehension of this. And we'll do a little bit, too, of notes here that will make it hopefully solidify a little more for you. So let's take a look at another example. Suppose we have this semicircle, which we've discussed in the past, which is the square root of 4 minus x squared. Well, this is a circle whose radius is 2. It's only on the positive part of the graph, meaning it is above the x-axis. So here and here and here, and it's a perfect half circle. There it is. Now, what they will do, too, is they will show you your limited or your domain of this function, which is from -2 to 2. These are your x values. It says this function is only defined under the domain of the x values falling between an x value of -2 and an x value of 2. Now, if I wanted to check for continuity at the endpoints, I can see continuity through this whole arch, okay, because I can draw it if I could draw it nicely. I can draw it without picking up my pen. But let's take a look at the two endpoints. If I look at the left endpoint and I want to find the limit, when it's at an endpoint, you only have to find a one-sided limit. So here, I would say as x approaches -2, coming in from the right side, which puts a plus sign up there as a superscript above it, the limit of this function as x is approaching -2 from the right side is a height of 0. So now, if it's truly continuous, if I want to prove it being continuous at an x value of -2, then f, the function value at an x value of -2, it better also equal 0. The function better equal 0 also. And the function value is the value of the filled circle, which is 0. So if these two guys are in agreement on an endpoint, then we say, or we can kind of prove it by the definition, that this is continuous. So this function is continuous at the left endpoint. Continuous at that left endpoint. So when you're looking for the endpoints, you're really only calculating the one-sided limit at an endpoint. Okay, the other endpoint would be over here at 2. So if I wanted to know if it was continuous on the right side, I would have to say, well, what is the limit of this function as x is approaching that right endpoint of an x value of 2 coming in from the left side? So coming in from the left side, the limit is 0. The height of the function at 2 is 0. Now, for it to be proven, we can see that it's continuous, but to prove that it's continuous, then we would have to also say that the function value at x equaling 2 better also be 0, and it is because that's where the hole is filled in. So under these conditions, we have now proven that this function is continuous at x equaling a positive 2, which we're really trying to emphasize at an endpoint, and this is the right endpoint. End point. Okay, so that's really getting right down to the nitty-gritty, proving that it's true. We can see it true by the graph, but that proves it algebraically. The limit, the one-sided limit, and the function value must be equal at an endpoint. Now let's do a break in the graph. Maybe this will be a little better. Suppose we have this graph. Suppose you're coming in from the left with the hole, and then you fill a graph hole, and then you go to the right. So we will, this is my x-axis, and this is, here we go, this is my x-axis, and this is my y-axis. I don't know how to make that look better. I don't think I made it worse. Here's the graph, and here's the graph. Okay. So let's take a look at the things that are happening right here at the origin where x is 0. And we'll name this function g of x instead of f of x. Just out of curiosity, would y'all know how to write that function? This would be a piecewise function. How do we write piecewise functions? How do we do this? Let's see. It's g of x, right? Okay, let's go up 2 units. This is up 2, okay? So how about g of x equals 2 when x is greater than or equal to 0? Is that what you said? Okay. And it equals a height of 0 when x is less than 0, right? That's how you would name the piecewise function. It's in 2 pieces. So what am I doing when I write 2? Really, when I put this here, really what I'm saying is y equals 2. Okay, y equals 2 when x is greater than or equal to 0, and y equals 0 when it's less than 0. So it's a broken function. It is a piecewise. Okay, so let's look at the problem and come up to see if it's continuous. Well, we know it's not continuous, but let's tell you why it's not continuous. Okay, so the limit as x is approaching 0, okay, say from the right of this function, what does it equal?
Equals 2.
2, okay. The limit as x is approaching 0 from the left of this piecewise function equals 0. Now, walking away from a limit, stop thinking limit, think function value. What is g of 0? What is the value at the filled-in circle? It is 2. Well, first and foremost, because this is an interior point, this x equaling 0 is an interior point for this graph. It's not the end, it's in the middle. So by this definition, the interior point here, these 2 limits don't even agree. So the limit, the 2-sided limit as x is approaching 0 does not exist. So we got a double whammy here. If this thing is continuous, this 2-sided limit better be in agreement with the function value. And they are not equal, so we can state that we have now proven that this function is not continuous when x is 0. Okay? So but because this statement and this statement are not the same, that is my proof that it is not continuous at x equaling 0. Now it's continuous everywhere else, but that one little place, that one little x value from negative infinity to infinity, that one little place in the graph, it's not continuous. Everywhere else it's good, but not right there. And there is my proof stating why it cannot be continuous at that point. And it's very obvious when you look at the graph that that would be how you would actually prove your point. Okay. All right, I can get this off of here. Okay, so let's do another example. So I can find the top of my piece of paper. There it is. Okay, so now having kind of looked at that, we're going to look at what the formal, not just casually talking about this, the formal continuity test. And this is in your book on page 75. And pretty much what it says is a 3-part requirement. And I'll write a lot of this down for you. This is on page 75, and there it is in the box. Continuity test. A function is continuous at an interior point, some point where x is some number c, if its domain, if and only if it meets the following 3 conditions. F of c must exist. The function better exist at the point. There can't be a hole in the graph there, or a vertical asymptote or whatever. The limit of the function, the limit as a 2-sided function, must exist, and the limit must equal the function value, which is what we have been doing. Those 3 things, the function value, the limit at the point, and those 2 better be in agreement. They better be the same. That's how we test something to see if it's continuous. We can look at it and say yes or no, it's continuous. But if to prove it, we would have to prove those 3 points. So, and I'm going to write that down, so don't rush through trying to write it down. So the three things are that f at the point has to exist, the function value at the point, the limit of the function where x is approaching that c value better exist, and these two guys better be the same. They better equal each other. So to write that they're the same, to write that down would be to say that f of c equals the limit of f of x as x is approaching c. That's the statement. They better equal. They better be the same. So visually, when you see that c, think of a number. Okay, c. Maybe c is 2. I'm 2 digits to the right. C would be 2 unless I said there was 10 units for every tick mark on my graph paper. Okay, but c is a number. Always think of c or k as just a number, like the number 2. So if your graph is moving along smoothly and continuously like that, okay, then for these three, to satisfy these three conditions, the first one is f at c existent. Yeah, f at c is a height of 3. Yep, that's good. Is the limit of f of x as x is approaching c, and we're kind of placing c like at 2. What is the limit of the function at 2? It's also a height of 3. Okay? So think of c. I'm going to leave c there because that's like the way the definition is written. That c is as if it's a 2. Okay? So the function value at 2 is 3, and the limit at 2 is coming to a height of 3 also. So these two guys are the same, which by the third standard of that test, we would write it that f of c equals 3, which, yep, is the same thing as the limit at that value. That's that third condition. So there's just trying to give you a more concrete example and still leaving the c in the position or in the example, and you should be replacing that c in your mind with the number 2 because it's just a number. Okay, don't let the x's and the c's and the a's and the k's throw you off. They're just numbers. So that would be that's kind of the first way of seeing it. Now look at it again. Let's give one where it's not going to work. Again, just really emphasizing this because to really prove it true, you got to understand these three conditions. So let c be here again as if c is the number 2. Okay, and put a filled in circle here and a circle up here. We already know there's a break. This thing is not continuous at that value c. It looks good everywhere, but boy, see, it's all messed up. But to prove that it's not continuous, I have to show that those three conditions do not hold. The first is, what is f of c? If this is 1, 2, 3, what is f of c? It's a height of 1. Okay, that's that filled in circle right there. Now, not talking about the function, but talking about the limit. What is the limit of the function as x is approaching c? This is where you're coming in from the left and the height is 3. You're coming in from the right and the height is 3. And so the limit equals the height of the graph at the whole, which is 3. Are these guys the same? No. So this is not continuous. So if you really wanted to write it down, you would say f of c, which equals 1, is not equal to the limit of f of x as x is approaching c. So there would be your proof of discontinuity. Not the same, I should put not continuous. Not continuous at c. Okay, so there's your 3-part test, proving it continuous or proving it not continuous at that point. You know, we never conclude anything up here at A. We should have said up here in part A, we should have said, hey, all this worked, so this means continuous. Continuous at C. That one worked. My word continuous never looks right. Continuous is what that says. Okay, there's your conclusion. Now, there's the algebraic prove it. Now, let's go back and let's look at some more graphs and state, this is not continuous and this one is, real simply. So this, I'm going to pull this as a bunch of graphs as opportunities to look at this continuity mess on the top of page 76, which is figure 2.40. Okay. And I believe y'all will see this very quickly. Looking at a graph and talking about continuity, when you look at the graph and you're thinking continuity and you're not thinking this algebraic three-part test, you're just thinking, do I pick up the pencil or not? So in this graph A, I'm graphing this. Do I ever pick up the pencil?
No.
It's continuous. Part B, oh, I got to circle it. Okay. I pick up the pencil. This one's not continuous. Part C, oh, I got a hole and I can move up here and fill it in and I pick up the pencil like crazy. Not continuous. Here's another one. We just did this one pretty much. We know that one's not continuous. You move along, you pick up the pencil, you fill it in. It's not continuous. This one, you go up here and you pick up the pencil and you pick it up and you bring it back down. Not continuous. And then here, what do they say here on part F? The function B through F are not. This is that oscillating like crazy situation. Okay? So this is not continuous. We don't like the oscillating mess, and I won't be testing you on the oscillating mess, so you don't worry about the oscillating mess, but it's not continuous. So there's you some kind of, and we've already discussed this, y'all made this conjecture for me early in this lecture where you said these are where you're going to have problems, and there it's showing to you these same issues. So a continuous function is one that is continuous at every single point in the domain. This one's continuous everywhere. This is continuous everywhere except when x is 0. This one's continuous everywhere except when x is 0. This one's continuous everywhere except when x is 0. This one's continuous everywhere except when x is 0. Because that's the place where you pick up the pencil. Then they do something quite interesting as they move along, but let me make certain I'm staying in sync here with my notes. Now I'm going to show you another thing, and I'm not going to emphasize this too hard because they make a lot of emphasis in the book, but when you're doing the homework, they don't really talk about this. Okay, so we're going to look at it, but they don't really go into any detail. They don't push this in homework. But there's a little bit of a tricky situation here, and this tricky situation is explained in example 5, also on page 76. And I'm not going to emphasize this because they don't use it at all in their homework whatsoever. I have not seen anything in their homework that's going to address this situation. I'm going to show it to you, but don't put a whole lot of weight on this, or don't worry about this because you're not going to see it. This is really interesting. Right here, the function y equaling 1 over x, which you can see is graphed here, and it should have arrows on the ends of all this, is a continuous function. They say that function's continuous. End of story, is continuous. Because it is continuous at every point in its domain, and x equaling 0 is not in the domain of the function. See what they're doing? So they're saying it's continuous, period, under the condition that you define the domain excluding 0. But that's, all of a sudden they throw this in, but we're not going to worry about it. But that's kind of weird that they put that in there, and it's interesting. But if they give you something like this, and they ask you a question like this, and they better play around and say, the domain is, and x equaling 0 better not be part of that domain if they want you to answer the question that that function is continuous. All right. Okay, so now let's look at, so instead of looking at graphs, let's look at some equations of some graphs and see if we can determine from the equation if it's continuous or not. Oh, I'm supposed to scan that piece of paper and I'm ripping it all apart. Okay. Here we go. So to determine if the following functions are continuous, or determine where. Determine where the following functions are continuous. And then they're going to give you some functions like this. We'll call it part A. Suppose it's f of x equaling 1 over x minus 2 minus 3x. And you are going to be really quick at this because we've already had a review about these things. I have no clue what the graph of this looks like, but I can tell you there's one problem. There's a vertical asymptote somewhere. Where is it?
2.
At 2. So I guarantee you this function is not continuous at x equaling 2. That's the only problem we have with it. So we say it is continuous everywhere except at x equaling 2. It's that simple. And they're going to ask you these questions in your homework. It's that simple. Do what?
They ask you, like, say, like, what the coordinates, like,
Oh, they're going to ask you a domain? So where is it continuous? You want to write it in interval notation?
yeah, they're asking you to write, I'm looking at it right now, and they're asking you to do it in interval.
Oh, okay. So how do we do that?
It's like, wherever the asymptote's at, it's like negative infinity to that, and then,
There you go. So everything but 2, right? So everything but 2. So it's negative infinity to 2 in union with 2 to infinity. But you put parentheses on the 2, because if you put parentheses on the 2, it's not including the 2. Okay, I know y'all seen that before. So if this is called interval notation. So if they ask you to write it as an interval, there it is. Closed brackets means union. All right, you don't get to use that number. Okay, so we'll do another one like that and put it in interval notation. What if our function looks like this? X plus 3 over x squared minus 3x minus 10. Okay, the question is to determine whether the following functions are continuous. Well, this one's bound to have some vertical asymptotes, but I don't know, it might be a whole, but regardless, if it's a whole or a vertical asymptote, it's going to be not continuous, or it's going to be discontinuous at that point. So this is x plus 3 over, what is this, x minus 5 and x plus 2. Okay, so we're going to say it's continuous everywhere except where? X equals 5 and x equals a negative 2. Okay, so how do we write this as an interval?
negative infinity to negative 5.
Hold on, it's a positive 5. Negative infinity to a negative 2. In union, that little U stands for union, or collect all this stuff together. Negative 2 to 5. And 5 to positive infinity. All right, let's put a trig function up here. Suppose we have h of x equals x plus 2 over cosine of x. Continuous everywhere except where is cosine x equal to 0? Pi over halves, and then again at 3 pi over 2, and then again at 5 pi over 2, and again at 7 pi over 2, right? So can we put, how would we write this? Can we put n pi halves, where n is odd, is an odd integer, odd integer. And I could not put that interval notation. They better not ask interval on that one. No, that's not going to happen. Okay, what if it looked like this? Now remember this, it's been a while since you've had trig. That's a cosine. My S never has the little point on it. Like Spock's ear, right? Don't know where that came from. Okay, so continuous everywhere except let's see. The problems occur when cosine of 3x equals 0, right? So 3x, which is theta, when does that make, cosine of theta equals 0, what must theta be? Oh, go ahead. Okay, where is cosine equals 0? Cosine equals to 0 at pi halves, just like up here, right? Same things. So now if I want x, what do? Divide everything by 3. So this becomes pi 6, 3 pi 6, right? 5 pi 6. So it's the same thing, but we call this what? N pi 6, where n is an odd integer. This is kind of a weird looking one, but it's not hard. Suppose it says this, 1 over the absolute value of x plus 1 minus x squared over 2. What a weird looking function. Is it ever possible to have a problem? Meaning, can the denominator ever equal 0? Or can you have a square root of a negative number? Those are our major undefined situations. Is it ever going to happen here? No. I'm never going to get a 0 in a denominator because even if this were negative 1, the absolute value of negative 1 is positive 1. So never will that denominator be 0. So this is continuous everywhere. It looks really awful, but oh well. I can't make an undefined situation, so it must always be continuous. Now, they're going to play around with you a little bit more on piecewise functions, so we need to get y'all comfortable with piecewise functions. We're going to see quite a bit of this in this section. Okay, suppose we have g of x equaling piecewise. It equals x squared minus x minus 6 over x minus 3 when x does not equal 3. Everywhere but where x equals 3. And then it just happens to equal 5 when x does equal 3. So I wonder what in the world this thing looks like. Okay, this is bound to be a hole in the graph, right? So let's think. This is what? X minus 3 and x plus 2, right? So we could cancel the x minus 3's, which means there's a hole. Okay. So really, this function value, maybe I should write it down here. So if I get rid of the hole, this is approximately, I'm going to put the squiggle equal. It's not the same, but close enough. It's approximately the equation x plus 2. So it really looks like that linear graph, with the hole in it at 3. So there's a hole at 3. Now, for this thing to be continuous, that hole has to be filled when x is 3, right? So what is the height of that hole when x is 3? It's 5, right? So this is good. So the height of the hole at x equaling 3 is by putting a 3 into this expression. Okay? So what does g of x look like? Well, g of x, which is this awful rational, looks like x plus 2, right? Looks like this. But it's got a hole right here. Where x is, so it's got a height of, what did I do? I'm way off, a height of 5. Okay, so over here at 3, there's a hole at a height of 5. So, I shouldn't have put this number here. Get rid of that. So, when x is 3, the hole is a height of 5. So this piecewise function, for it to be continuous, I have to fill in that hole. And the way to fill in the hole is say, let the function equal 5 when x is 3, which will fill in the hole. And that makes it continuous. So that does make it continuous everywhere. It had a hole. This one has a hole in it, but this one filled the hole. So together, they made a continuous function. Now, some interesting properties of continuous functions, which you're really not going to see any questions on any homework or test, is going to be what they have Theorem 8 on page 76. And we'll just look at this very quickly. It talks about functions that are continuous. Here it is right there. Properties of continuous functions. If f and g are both continuous functions, then the following combinations are true. The sum of the two functions would be continuous. The subtraction of the two functions would be continuous. A multiple of the function would be continuous. Multiplying the two functions would be continuous. All these would be continuous if f and g are also continuous. So that's just kind of, that makes sense. Okay. So, and then also it talks about the composition of the functions over here. If f is continuous at c and g is continuous at c, then the composite of the functions is also continuous. So talking about composition of your functions being continuous if the two functions are originally continuous. Okay, so we're going to get a little more into depth like that last example we did. But before we go into a little bit further, we're going to talk about various types of discontinuities. And they name these things. So where it is not continuous, it is discontinuous, and it has a discontinuity. Okay, a big word, a discontinuity. Okay, so you just need to hear the words. I know you understand what they are, but you need to hear them. You have what they call a jump discontinuity. A jump discontinuity. This is where you have a break in the graph, which causes the graph to be discontinuous. A jump discontinuity is where there is a break in the graph. A break in the graph makes it not continuous. Okay, so a jump discontinuity is where you have a break in the graph. What do you think an infinite discontinuity is? There you go. There you go. That's a big word. Discontinuity, that's a big word. Infinite discontinuity, there's a bunch of I's in that. Infinite discontinuity is where there's going to be a vertical asymptote. Do what? Discontinuities. Infinite discontinuity, that sounds really impressive. There was an infinite, we talked about infinite discontinuities today. Okay, and then we have the ones that we're not going to deal with. That's how I spell this right. Oscillating discontinuity. Of course, that's just explains itself. Oscillating discontinuities. And then the ones that we're going to emphasize are the removable discontinuities. Okay, this is the good one. The removable discontinuities. These are the ones that we're going to play with. the removable discontinuities. Okay? Usually the removable discontinuities are discontinuities caused by a hole in the graph. Usually a hole in the graph. Now, not a break, but a hole. No breaks. Okay? No break in the graph. No break, but just a hole in the graph. In other words, we can fix the hole in the graph. We can fill in the hole in the graph and make the function continuous, as we did in that prior example with that piecewise function. So we can usually remove a discontinuity if there is a hole in the graph. Okay. So for a quick example, if I look at the example 2.40 in the figure 2.40b, which must be on page 76 again. Okay, this would be an example where we have the hole in the graph and we can fix it. Okay. This one has the hole and I can fill it in and fix it and make it continuous. If there's a jump, that's a problem. You have to redefine that function. This one, it's a bad break. You know, I can't do that. Vertical asymptote, I can't fix that. But this one I can fix by naming it a piecewise function and filling in the hole. Okay, name it a piecewise function and fill in the hole. That's what we're going to do to fix a removable discontinuity. Okay, so let's make this happen. This will be part D. Okay, so here we go. Suppose we have your function equaling x squared plus x minus 6 over x minus 2. Either this thing has a vertical asymptote of 2. Either this thing has a vertical asymptote of x equaling 2 or a hole. So the only way we can figure that out is if we factor it. So if we factor it, this would be what? X plus 3 times x minus 2. So we've just determined that if I can cancel, then it's a hole in the graph. So in other words, there's definitely a hole. So this should be something I can fix. So what this graph looks like, I'm going to put this similar little squiggly. It's not really equal, but kind of is. This graph looks just like x plus 3, but there's a hole in it at the x value of 2. So if I were to graph y equaling x plus 3, one, two, three, 1, 2, 3, 4, 5, 6. When x is 1, we're up 4. Darn. When x is 1, we're up 4. When x is 2, we're up 5. When x is 3, we're up here. Okay. And at x equaling 2, we have a hole in the graph. I should try to do this in a pencil, but it doesn't display well. That's a hole in the graph. I didn't do that worth a darn. I need some whiteout. That's what this graph looks like. I can graph x plus 3, that linear graph, and put the hole at 2 in the graph, and that is the graph with the hole in it right there. So it is discontinuous because it has a hole. If I want to make it continuous, I need to fill in the hole. And when I fill in the hole, how high is it? It's at 5. Okay? So here's how I'm going to fix it. I'm going to rename this function piecewise. I'm going to say, okay, leave it alone and let it be its lovely little x squared plus x minus 6 over x minus 2. Let it be that. But don't let it be that when x is 2, because there's a hole in the graph at 2. So when x equals 2, what does this height need to be? 5. Now we have removed the discontinuity, or we have filled the hole. This one is continuous everywhere.
So it's just what, would it be just as what they name it as? Like if they give you the top one
So yeah, they give you this.
and ask whether or not that is continuous?
They want you, well, you're supposed to be able to figure out it's not continuous.
Well,
Because
okay.
it's not continuous, so they want you to write it so it is continuous everywhere.
So it's defined as not continuous.
Yeah. So remove that discontinuity, and this removes it. So remove the discontinuity by rewriting the function so that you fill in the hole. Okay. So let's do another one similar to that. I'm going to make y'all factor. Yes. Make you guys factor this sucker. Okay. Suppose that g of x equals, I know y'all love this, x cubed minus 27 over x minus 3. Okay, y'all remember both of those lovely formulas? I cannot walk away from the camera. I'm not supposed to use that board. Okay, let me see here. You have these two that you're supposed to kind of have ingrained somewhere in your brain. That x cubed plus b cubed is a cubed plus b cubed is factored as a plus b times a squared minus ab plus b squared. And the other one is a cubed minus b cubed is a minus b times a squared plus ab plus b squared. Those are your two formulas for factoring a sum or difference of cubes. So we have the subtraction version, and everywhere there's an a, we're going to replace it with x, and everywhere there's a b, we're replacing it with 3, because this is x cubed minus 3 cubed. So everywhere there's an a, I'm putting an x, and everywhere there's an b, I'm putting an 3. Everywhere there's an a, I'm putting an x, and everywhere there's a b, I'm putting a 3. So there it is. So this is x minus 3 times x squared plus 3x plus 9. So this is x minus 3 times x squared plus 3x plus 9. So you're going to get, of course, if we're going to have a removable discontinuity, we better factor this so that we can cancel out or come up with the whole. So this is approximately equal to the x squared plus 3x plus 9 parabola. So if you were to graph this, it's going to look like a parabola, but there's going to be a hole in it when x is 3. Maybe I should graph with my calculator, because I didn't graph that linear graph well at all. That was really not good. So here we go. Let me see if I can graph this sucker. In Smart View, seems like it runs so slow. Okay, here we go. So I'm putting in here, I don't know if we get all these screens on here. Okay, y equaling, I cannot do this. I can't put both screens. I don't think I can see it. Nope, I can't. Ooh, I know what I just did. I made a mess. Okay, so this is going to be x squared plus, hold on, I'm going to change it. Let's put the whole thing in here. Parentheses, x cubed, x, math, cubit, x cubed minus 27 divided by x minus 3. X minus 3. Okay. And I'm going to do a zoom. I think that says zoom right there. Standard on this graph. Down, down. And there it is. And that's not a good graph, because I need it to go higher, don't I? So I'm going to change my window a little bit more. And I'm going to get a Y max in here. I don't know, maybe I need this to be 30. There it is. So it's a parabola. Okay, that awful rational function is just a parabola. But where x equals 3, there's a hole in it. So let me see. Let me trace it. I bet it's not going to trace very well. No, it's not going to trace. Let me do a second, I can't read these words, calc value and put a 3 in. Normally, if I put that in there and hit enter, it's going to tell me the y that matches that ordered pair. But it's not going to be there because there's a hole in the graph there. Okay, so that's verification that it's not really a parabola. Almost is, because there's a hole in the graph. And it can't even tell me the vertical value because it's not, can't do it because it's non-existent. So we know what the graph looks like. What is the deal with the red on here? How do I get that to go away? Anybody got any idea what I just did?
I think it's your writing cursor for it.
I wonder how I get that off. I've never done that before.
Yellow thingy. Oh, the one that you moved out of the way. No, left.
This?
Yeah.
What did I do? Go back to this?
Delete all.
Yeah, just those
Which
two.
one of those is delete all? Do y'all see it? Aha.
That's it.
Yes. Thank you. All you technological people. Okay. Okay. So this sucker, this little lovely, awful looking rational expression is something like this, but there's going to be a hole. Okay. Now to get the value of the hole, what in the world is the value of the hole? This is this parabola, the same thing. This rational equals this lovely x squared plus 3x plus 9, except for at 3. So I put the x value of 3 into this version of the rational function to come up with the height of the graph. So these two are exactly the same, except this one has a hole in it at 3, and this one does not have a hole in it at 3. So I use this one to determine the height of the graph at 3. So if I put a 3 into this, this is going to be 3 squared plus 3 times 3 plus 9, which is what? 9 plus 9 plus 9, which is 27. So this ordered pair is 327. So the height of that graph at the hole is 27. So to fill it in, I need a y value of 27. So here we go. Now we're going to take this function that has a discontinuity at 3 and rewrite it so it's always continuous. So I'm going to write it as a piecewise function. I'm going to let it be itself, this rational. It can be this everywhere except where x cannot be 3. And then at 3, what do I want the height of the function to be? 27, where x equals 3. And what this just did is made this continuous everywhere because it fills in the hole. Okay, because it fills in the hole. Now, does that make a little more sense? I did it nice and slow and easy, hoping to help you follow that. Because it's pretty important that you follow that, because the next question requires you to understand this one. Okay? So I hope that gives you a nice visual. Okay, so this next one's fun. But you got to be thinking. Okay, so it says, here's the question. For what value of A is f of x continuous? Oh man, I messed up. They were continuous, whatever, everywhere. And here's what it looks like. Ax squared plus 2a when x is greater than or equal to 2, and 12 when x is less than 2. Okay. So it's as if this, Okay, here we go. What this function sort of looks like is if x is 2 here, and suppose this is way up here at 12, okay? To the left of 2, this is a horizontal line at the height of 12. And at 2, it's an open circle. To the right of 2, it is a parabola. And I don't really know what the parabola looks like, but I don't know, just act like it's doing this. Okay? So on the left side of 2, it's a horizontal line. On the right side of 2, it's a parabola. Now, I need to fill in the circle here. So I need to write this equation so that it fills in that circle at a height of 12. In other words, I want this ax squared plus 2a, I want it to equal 12 when x equals 2. I want the height of the function to equal 12 when the x value is 2, so it'll fill in that circle right there. I want ax squared plus 2a to equal 12 when x equals 2. Well, if that's the case, this x can be replaced by 2. So I take this x and I replace it with 2. So this becomes 4a plus 2a equaling 12, 6a equaling 12, or a equaling 2. So if this had been 2x squared plus 4, it would have filled in this hole at a height of 12. Okay? Now that's if you understood the last example, this would make sense. So you got to kind of get the vision of this to understand. When you just have a constant here, this is representing the equation y equaling 12, which is a horizontal line at a height of 12. That's all that is representing the equation y equaling 12, which is a horizontal line at a height of 12. So you got to kind of get that vision to understand how this fits together. Okay, now, how about we take a break? We don't have a whole lot left to do, and what we're getting ready to do, the textbook does it a lot harder than what I do it. It's looking at the calculator to make it happen. But let's take a break, and I'm going to pause this recording. Okay, so let's finish up this section. Let's find there it is. Okay, and the last part of this section is going to be what we call the intermediate value theorem. And this is not difficult because we can use our calculators to make this very easy. But you really must understand the concept underneath it in order then to be able to use your calculator and get it all to make sense for it to you. So I'm going to actually go straight to the book and I'm going to read the theorem and let you think about it and see if you can put into English terms what you think this theorem on page 80 is trying to say. And it's not that complex. Now, the wording may be complex, but the theorem itself is really stating something quite simple. And there it is. Yes, I sure can. And there it is, the intermediate value theorem. If f is a continuous function, so that we're going to have a function here, that it better be smooth and continuous with no issues. So you got to think of that right now. Just transition from all the problems to a nice, pretty, perfect continuous function with no breaks, no jumps, no vertical asymptotes. It's just nice. So if it's a continuous function on a closed interval between two x values, and they're using a and b as x values, like maybe 2 and 10, and if y sub 0 is any value for y between f of a and f of b, then y sub 0 equaling f of c for some c in the interval. Think about that for a minute. It's really simple. It's kind of like, why do we need this? What's the whole reason for this? Anybody have any clue what they're trying to say? First of all, this point right here is the point a, f of a, right? And this point here is the point B, f of B. So your height of your graph is f of A here at this end point, and your height of your graph is f of B at this end point. So they're picking some random value C, some x value C in this interval, any x. They're using the number C. And they're saying if I pick some C, then it's going to have a height of f of C. That's all it's saying. That's it. That's it. I don't have anything else to say. That was the end of the sentence. That's it. There is no major point. Okay. The point is that if this function were not continuous, we couldn't say this, because if there had been a hole in the graph, you couldn't make this statement. Do you see that? Had there been a hole in the graph, we couldn't make this statement. Or a vertical asymptote. There you go. Or a vertical asymptote or whatever. So because it is continuous, we can say that. Yeah, they don't even have to say that f of C is between f of A and f of B. You don't even have to say that. It's just there. It just exists. Any C that you pick, it better have a Y value. An existing Y value. That's all there is to it. Because it started with saying it must be continuous. That's it. Okay? So, pretty simple. So let's see what it says. Geometrically, the intermediate value theorem says, now this is a little harder to understand, in my opinion. Geometrically, the intermediate value theorem says that any horizontal line at a height y sub 0, instead of saying f of c, they're saying y sub 0, any horizontal line y sub 0 crossing the y-axis between the numbers f of a and f of b will cross the curve at least once. I don't think that's a very good geometric description of this theorem. But then it finally says down here, if f is discontinuous at even one tiny point in the interval, then the theorem's conclusion may fail. So, right, that could be that one point from negative infinity to infinity that there is an issue. Okay, so what else is so great about this? Where we really use this is we use it when they start talking about down here a consequence for root finding. This is where we really apply it. We call a solution of the equation f of x equaling 0 a root of the equation or a zero of the function. The intermediate value theorem tells us that if f is continuous, then any interval in which f changes sign, it must contain a zero of the function. Okay, let's talk for just a minute. That's the big deal right there. That's where it all starts making sense and where it becomes useful. Okay, one of the big things we have to get straight, when they start talking about the root of a function, they also call it the zero of a function, which is what? It is an x-intercept. It is where your graph crosses the x-axis. We use those words interchangeably. The root of the function or the zero of the function or the x-intercept of the function, they're all the same thing. So what we're saying now is that if you have a function, I don't know, maybe it's doing this, okay, if this is what your function is doing, and it is continuous, this right here is your zero or your x-intercept or your root, where it crosses the x-axis, which is also where, if this is f of x, this point, which is the zero or the root of the x-intercept, is where the y value of the point equals 0. Focus, camera. Okay, right? Do y'all agree? Everybody agree with this so far? So what the intermediate value theorem is going to say is if this is a continuous function, if you pick an x value to the left of that point, suppose x is 1. At the point 1, your function value at the point 1 is down here, right? F of 1, I don't know what it equals, but it's going to be a negative value because it's down below the x-axis. So f of 1 is negative. If I pick a point over here, say it's the point 4, f of 4, is it positive or negative? It's positive. So if the function is continuous and it changes from negative to positive or positive to negative, then there must be a 0 or an x-intercept or a root involved between those two values, because you can't break the function. It's got to be smooth and continuous. So we can prove that a root exists. Even if we can't algebraically come up with the value of the root, we know one must exist if the function is changing signs from negative to positive or positive to negative, because it's going to have to cross the x-axis. So we can prove a root or a 0 of the function or an x-intercept exists in a certain interval if that function changes sign. That's where we really use the intermediate value system. So if they change signs, if a change in sign then a 0, which is also referred to as a root, which is also referred to as an x-intercept, must exist. And we use those words interchangeably. I don't know why, but we talk about zeros of the function all the time. We talk about the roots of the function. We use those words all the time, and all that is talking about where your graph is crossing the x-intercept. So nail that simple understanding before we now go in here and talk about how to do this. So here's where it's easy if you understand the logic of what in the world the intermediate value theorem is doing, which is going to help us find a 0 of the function. We are always looking for zeros of functions. Okay, so here's how we're going to do this. Here's where we're going to apply it. Show, that's an S, show there is a root. And remember, a root is a 0, is an x-intercept. All those words mean the same thing. Show there is a root of the function, and here's the function, x cubed minus x minus 1. Actually, we should call this an equation, not a function. We're supposed to call this an equation because it's not written as f of x. It doesn't have a y value. Between 1 and 2. Now our calculator is going to make this nice and easy. What I'm going to do is replace the 0 with f of x, which is the same thing as y. And I'm going to first go in here on my calculator and graph this thing and see if it really does cross the x-axis between 1 and 2. And if it does, then I'm going to prove it algebraically is true using the intermediate value theorem. Okay, so we're going to cheat. We're going to use the calculator to prove that, yeah, it's going to happen. Then we're going to go back through the intermediate value theorem to show it algebraically as being true. Okay, so between an x value of 1 and 2, so let's take a look at the calculator. And put in here, go to the y menu, clear what was there, and put in here x cubed minus x minus 1. And I'm going to graph it, and I'm going to do a zoom standard again and see if this works. Zoom, there it is, standard. And I'm looking between 1 and 2, which means look at the x values between 1 and 2, which I think this is a 1 and this is a 2. And I can make it a little smaller, couldn't I? I guess I could do a zoom decimal. That's a little window. There we go. Most definitely between 1 and 2, there is an x-intercept or a 0 or the root of the function. Okay, do y'all know how to get the value on the calculator? We can find it. Go, oh man, I can't see these things. Second, calc. Actually, I just do the 0 of the function right there. 0, find the 0 of the function, which is the same thing as the root, which is the same thing as x-intercept. And it's going to ask me it's going to ask me 3 questions. It's going to ask me a left bound, a right bound, and a point of guess. So left is just be to the left of the x-intercept, about right there. Hit enter. Right is to scroll to the right side of the x-intercept, about right there. Hit enter to answer it. And then guess it right on. enter, and that x value is 1.324718 rounded off, okay? So we're kind of cheating, like major big time here. But it's okay. Right. So we know what's happening. So now let's go back to our piece of paper. I got to write this down. Really, this is 1.32. Okay. So we know it is happening between 1 and 2. So using now, we got it. So we saw it. We saw it on the calculator. That's what it looks like. We know it's happening. Now to prove it by the intermediate value theorem, this is really easy. Okay? By the intermediate value theorem. We know this function is continuous because it has no places where it can be undefined. It has no zero denominators or mess like that. So all we have to do is when x is 1, let's compute f of 1, which means put a 1 in here. If I put a 1 in here, this is 1 cubed minus 1 minus 1, which is 1 minus 1 is 0 minus 1 is negative 1, which is a negative value. If I put the other endpoint, which was a 2, so if I computed it 2, it is 2 cubed minus 2 minus 1, which is 8 minus 2, which is 6 minus 1, which is 5, which is positive. So since the function is smooth and continuous, and it changed signs between 1 and 2 by the intermediate value theorem, there must be a root between 1 and 2. So because a change in sign a root, a 0, an x-intercept exists between x equaling 1 and x equaling 2. Got it? Pretty easy, isn't it? Right. I don't care what it is. It changed signs. It had to have crossed that x-axis. It went from a negative to a positive because right here was your negative y and up here was your positive y. And so you went from a negative y value to a negative 1y value to a positive 5y value. You had to have crossed the x-axis. And it didn't jump because it was a continuous function. It couldn't jump. It couldn't break. It was a continuous function. Pretty easy, right? I could have expanded the screen. That is so hard for me to remember to do. Very, very, very simple. Okay, so now let's get a little bit harder. Not bad. Okay, a little bit harder. Okay, so use the intermediate value theorem. You are going to get really tired of writing the words intermediate value theorem. To prove the equation has a solution. And this one's a little uglier now. Okay, this one is the square root of 2x plus 5 equaling 4 minus x squared. Now the first thing you have to do is make this thing equal to 0. Because when it equals 0, you're going to replace the 0 with y. And when y is a 0 value, you're at an x-intercept. So I'm going to rewrite this as the square root of 2x plus 5 minus 4 plus x squared equaling 0. Now if I replace the 0 with f of x, that means f of x equals 0, which means y equals 0, which is going to be on the x-axis. So this now is the square root of 2x plus 5 minus 4 plus x squared equaling my f of x. So I'm looking for the root or the x-intercept of f of x. So I'm going to go to the calculator. I'm going to cheat a little bit by going to the calculator and graphing this and seeing where it crosses the x-axis, where it really does have a root. And then I'm going to pick a number to the left and a number to the right and show that it changes signs algebraically So there must be a root or a zero of the function at that location. Okay, so go to your calculator, and this is not going to be quite so easy to type in. Be certain you get your parentheses in the right place. So we have the square root of 2x plus 5. 2x plus 5. Close parentheses, close information under the radical. Then you're going to do minus 4 plus x squared. I need to graph it. I'm going to go back to a Zoom standard to graph it, which takes it from a negative 10 to a 10. Okay, this one has more than one x-intercept. Why in the world does the graph stop right there? Is there something wrong with my calculator? It's not an error. We're getting close about the what's the imaginary miss all about? There you go. Right here, if your x value causes this stuff under the radical to be negative, then it's not going to be in this real number system. Okay, so it's limited. Right here, it's limited because anything to any x value to the left of this, like negative 10, is going to make this the square root of a negative, 15, which is not a good situation to be in. Okay, so your domain is being limited by that radical, making that, what is that called, a radicand? It has to be positive. Okay, so this thing has two zeros. So there's two roots to this equation, and we can go in here very quickly and find them. Second calc, zero of the function. We can find both of them. So get to the left of it. Left bound is to the left of the left one. Hit enter to answer it. Right bound is to the right of it. Hit enter and guess it kind of right on as close as you can get to it. And there it is. And I would do a rough sketch on my paper and mark what that is. And it's approximately a negative 1.6. Okay, now let's go get the other one. Second calc, 0. And let's scroll over there to get near it. To the left of it is going to be approximately, I don't know, somewhere in this region, close enough. Enter. To the right of it, enter, and guess it as close as you can get. And then your other zero of your function is approximately 1.14. Okay, so we can show two roots to this one.
So do you do that just to narrow down?
Yes. To narrow down where I'm going to find a change in sign to prove it happening by the intermediate value theorem. Okay, so, wrong one. Okay. So I kind of sketched it roughly. So there's two roots. So right here, if I pick a number, so this is the first root. If I pick a number to the left of a negative 1.6, is it going to be positive or negative? It's going to be positive because it's up here somewhere. Okay? If I pick a number to the right, suppose I pick, what, negative 1, which would be in this region, right? Is it going to be negative or positive? It's going to be negative. Okay, we got to show that. You know how to do this on the calculator? You ever done this? This is nice. Surely y'all done this on the calculator. This is a can't be beat kind of option. You go back to your calculator. That function's still in there. Go to the home screen. Go to vars. I don't know, maybe I won't like this. Y vars. Get that Y1. I want Y1 evaluated at negative 2. And it equals 1, which is positive. If I want to evaluate, now I'm going to do a second enter, which is going to pull that last statement up. I'm going to replace it with a negative 1. Oh, I thought it was going to. I messed it up. Delete. Negative 1. And it's going to be a negative value. Okay, so back to my setup. F of negative 2 is positive 1, which is a positive value. F of negative 1 is about a negative 1.2, which is a negative. So this is a change in sign. So therefore, conclude a root between x equaling -2 and x equaling -1. There's one of the roots. Okay, the next root, there's one result, that's one part. The next result would be to what? If we're going to go to the 1.14, maybe we calculate f of 1 and f of 2, right, to get to each side of this number. Is f of 1 going to be positive or negative? F of 1, is it going to be positive or negative? It's going to be down here, it's going to be negative, and this other number better be positive. So I'm going to do this on the calculator. So right here, I'm going to pull this up again. Let's do, that's not what I wanted. Second entry. I want to do go over there, a positive 1. Well, that didn't work. Positive 1. Hit enter. It's a -0.35. And then I want to do a positive 2. Enter. And I get a positive 3. Go back to my, okay, so this one is negative. This one is positive. This is a change in sign. So once again, I conclude a root between x equaling, what have I done, 1 and x equaling 2 by the intermediate value theorem. So the intermediate value theorem doesn't seem like it says a lot, but it does. It tells me where a 0 exists. Helps me find the zeros on my function. And, you know, you would not want to try to solve this. Well, I guess you could solve this one. But lots of equations are much too hard to solve. Okay? They're much too difficult to algebraically solve by hand. In fact, it might not be possible. But the intermediate value theorem would let you state that there is a 0 there, that it does cross the x-axis. That is the end of this section. I want to give you this quiz. So let me close out this recording.